Hello students, welcome to the lecture series of operating system in which today we are going to discuss our topic dining philosopher problem. Before discussing our topic, let's discuss prerequisite for this topic. So the prerequisite are concept of process synchronization, critical section problem, semaphore and deadlock. So just quickly revise these topics and then we will move forward. Okay, let's discuss these topics quickly. Process synchronization. So process synchronization is a way to coordinating processes that use shared resources. We can say that suppose P1, P2, P3, P4 are the processes which are using a variable, shared variable A or a resource R, then we can say that we have to maintain the synchronization between these processes. Critical section problem. So what is critical section? Critical section is the code segment that can be accessed by only one process at a time. Basically, we can say that suppose A is the variable which is shared by two different processes P1 and P2, then the code segment in which we are using the variable A, that section is known as critical section. Semaphore. Semaphore are the integer variable that are used to solve the critical section problem by using two atomic operations, wait and signal, that are used for process synchronization. So basically, semaphore is going to use for process synchronization problem. Deadlock. Deadlock is the situation where a set of processes are blocked because each process is holding a resource and waiting for another resource required by some other processes. So basically the deadlock is a situation or a scenario in which every process is waiting for the another process to release the resource so that the previous process can complete its task. Okay, let's discuss dining philosopher problem. The dining philosopher problem is classic synchronization problem which is used to evaluate situation when there is a need of allocating multiple resources to multiple processes. So what we are going to discuss that we have multiple resources and multiple processes. These processes will request for these resources, but we have to maintain the synchronization between them so that there may be no situation of deadlock. Now, the dining philosopher problem states that there are five philosophers are sitting around a table and their job is to think and eat. What we are going to do, we are comparing our process synchronization problem with a real-time scenario. We are here, the philosophers represents the processes which are requesting for resources, and there are two jobs, thinking and eating. Thinking is the time when the process is waiting for the resource, and eating is the time when the process is using the particular resource. We can take any number of processes, but here we are assuming that there are five processes. So we are taking the example that there are five philosophers which are sitting around a table. Okay, the bowl of noodle is placed at the center of the table here, along with the five chopsticks for each of the philosopher. To eat, a philosopher need both their right and the left chopstick. Basically, chopstick represents the resources which is required to complete its task for a particular process. The philosopher can only eat if the both immediate left and right chopstick of the philosopher is available. In case if both chopsticks are not available, then the philosopher put down their left and right chopstick and start thinking. Basically, what this point is representing? This is representing that a process, suppose the process P1, for completing its for process P1, if the process P1 wants to complete its task, then it need two resources, this one and this one. But if the both resources will not be available, then P1 will not able to complete its task. So if P1 allocate the first chopstick, that the first resource, but the second one is not available, then it will release the first one also and start thinking again. What does that mean? That it is waiting for both the resources. Okay, let's discuss our solution of dining philosopher problem with the help of semaphore. Here, in our case, we are taking five philosophers, that is five processes. And the shared data is bowl of noodles, which is representing data set. Semaphore, and we are taking one array of semaphore named chopstick 5, initialized to 1. Basically, we have a chopstick array with all initialized value 1. Every value in this array is representing that all the chopsticks are currently available. Suppose a process P3 wants to complete its task. So P3 need chopstick 3 and chopstick 4 so that it can complete its work. Now let's try to understand this code. If the philosopher I, that is process 3, wants to complete its task, then it will request for chopstick 3 and chopstick 4. So for that, it will wait for chopstick 3 and 4. So wait chopstick I, that is chopstick 3, and wait chopstick I plus 1, that is 3 plus 1, 4 modulo 5, that is chopstick 4. So when the process 3 will wait for 3 and 4, then what will do? Then the chops value of this particular semaphore will be 0. And if that particular philosopher grant wait on both the chopstick, then it can complete its work, which are representing by eating process. After the completion of this work, the philosopher will release both the chopstick by signal operation. So when the signal chopstick I, that is C3, and the signal chopstick I plus 1, that is for C4, will be executed, then again the value of the semaphore will set to 1, and again these both chopsticks are ready to be used by any other process. Okay, let's quickly try to understand the code once again with the help of another example. Uh, Suppose a philosopher P0 wants to eat, it will enter the philosopher function and execute wait. Take chopstick I and hold C0 chopstick and reduce the semaphore C0 to 0. After that, it will execute wait chopstick I plus 1 modulo 5 and hold C1 chopstick. Since I equal to 0, therefore 0 plus 1 modulo 5 is 1 and reduce semaphore C1 to 0. So basically when the P0 wants to complete its work, basically P0 wants to eat, then P0 need chopstick C0 and C1, and it will gain these two chopsticks with the help of wait function for both of the chopsticks. Hence, the above code is providing the solution to the dining philosopher problem. Also, at one go, two independent philosophers can eat simultaneously. That is, a philosopher P0 need C0 and C1 for its eating process, and P2 need C2 and C3 chopstick for its eating process, so they both can do their work simultaneously. Similarly, P1 and P3 can eat simultaneously. Okay, now let's discuss what are the drawback of that particular given solution. From the given solution of the dining philosopher problem, we have proved that no two neighboring philosophers can eat at the same time, same point of time. How? Suppose P0 wants to eat, then P0 needs C0 and C1 chopstick. But if P1 wants to eat simultaneously, then P1 needs C1 and C2 chopstick. But you can clearly see that C1 chopstick is assigned to the process P1, so it will not be assigned to the process P1. The drawback of the above solution is that this solution can lead to deadlock condition. This situation happens if all the philosophers pick their left chopstick at the same time, which leads to the condition of deadlock, and none of the philosopher can eat. You can easily visualize this situation that suppose there are three processes P0, P1 and P2. Suppose P0 hold its chopstick C0 and P1 hold its chopstick C1 and P2 hold its left chopstick, that is C2. Now all the processes are waiting for the second chopstick, but none of the process is able to complete its task. So this is the situation of deadlock. Okay, to avoid deadlock, some of the solutions are given here, so we can follow any of the solution. So the first solution is maximum number of philosophers on the table should not be more than 4. This is for chopstick 5. That means if we have 5 chopsticks, then the philosophers count should not be more than 4. What will happen? So at least one of the philosopher will receive its both the resources and it will complete its task and release the resources which will be used by any other process, and the possibility of the deadlock will be resolved. The philosopher at an even position should pick the right chopstick and then the left chopstick, while a philosopher at the odd position should pick the left chopstick and then the right chopstick. So basically, this point will break the monotony that all the philosophers are picking their left chopstick. So what will happen? Any of the solution will receive both the chopstick, which is which is used for its work. Only the third solution is only in case if both the chopstick left and right are available at the same time, only then the philosopher should be allowed to pick their chopstick. So this is one of the solution. If both the chopsticks are available, then only any philosopher can pick any of the chopstick. Otherwise, it will wait for both the chopsticks. Okay, that's all for this topic. So we have discussed what is the dining philosopher problem, code of the dining philosopher problem, and what are the drawback of this problem and how we can resolve these drawbacks. Okay, that's all for today. Thank you so much.